Hi, in this tutorial we will study normalization, in which will be further analysis the tables that we have in a database design to find possible redundancies with the data that can lead some inconsistencies during insertion or deletion. And these problems can be caused by some functional dependencies, and that's what mainly we're going to study on this chapter. And the way that we usually normalize is that we split the tables into tables, and maybe a table can be further divided into two, three, four, or a number of tables to avoid the problems that I just mentioned. And I just will illustrate that with an example. So what we're looking for is what we're going to call high quality tables or good tables. So we don't want any, we don't want any bad tables that can have other problems. And as you remember, we were using the ER model as our first step on capturing the information that we got from the requirements for the database, and we got an initial design of the database. But there is a further analysis that we call normalization, and that's what we will study now. So here, for example, let's suppose here there are two alternatives to store the information about products and manufacturers. And so, for example, let's look for a moment on the second design that says product manufacturer. So we see that we got product number, which is identification, product name, price, manufacturer ID, manufacturer name, and address. And then on the other design, we have two tables. And on the second design, we got some problems that we will see that there is some redundancy, and that's what we will see on the next part. So for example, the name and the address of each manufacturer will be repeated. So let's see. So here, so we got product name and then here manufacturer. So what it means is if we have a manufacturer that produces more than one product, we're repeating that. And now what's the problem with the redundancy? Well, there is more storage and there is a possible inconsistency. Why possible inconsistency? Because we're repeating the same information. So when there is an update or a delete or an insert, we can have a problem because maybe the name of the same manufacturer doesn't match the name that we inserted on another record. And if we have a unique identification of the manufacturer, so it doesn't make sense to have that repeated multiple times. So the first design here, it looks better. So usually in the process of a normalization, we find a table that looks like this, and we find some type of redundancy. And for that, we're going to use what we're going to call functional dependencies, which we will study very soon. And we will divide and find this. Divide the table, and that's what we're going to call normalization, and that's the way that we avoid. So one of the problems that we say with bad tables is redundancy, insertion and deletion. So why insertion again? Because if like it's explained here, so maybe we have a manufacturer that it doesn't really provide anything a product right now, so there is no way that we record that information because we don't have that, or deletion if we have only one manufacturer and then we delete that record, that product, then we're losing that information too. Um, so the like I said, there were two alternatives there. So the first design was the good one. Now I will give you an additional example. This is one of the examples that I like. So for this additional example, I have a table teachers, and teachers I have an ID, name, date of birth, years of experience, height, degree, and salary. And then this is what we notice. I mean, first initially we said, well, what is wrong with this table? I mean, this table looks okay. Teachers, I mean, the identification of the teacher, the name, the date of birth, the years of experience, height, degree. The height degree maybe bachelor's, master's, or PhD, for example, and a salary. So maybe we got that from the ER, so it doesn't seem that there is nothing wrong. However, for this particular application, let's suppose that there is uh, some time of rule that says that years of experience, when you combine years of experience and the degree, you determine the salary of the teacher. For example, let's suppose that we can make a table that looks like the years of experience, 0 years of experience in a bachelor, 35,000, and then maybe years of experience in a PhD, 80,000. So that's what we're going to call soon functional dependency. So functional dependencies, we have a set of attributes that determine the value of another set of attributes. So in this case, years of experience together with the highest degree determine the salary. And that's what we want to define soon as a functional dependency. So again, by looking into the teachers table, it doesn't look that anything is wrong about the table, but then if we further examine some of the other constraints or rules over the data, we find out that use of experience, high degree, determines salary. So for example, in a possible instance of table teachers, here, for example, we got here 3 teachers that have the same years of experience, 2 years of experience, the first 3 teachers here, and they have the highest degree is a bachelor's, they all make 38,000. So you see that I circled that, that's what we call a redundancy. Now there is only one teacher here with 10 years of experience and a master's that makes 47. Now, the problems that we were discussing before, for example, there is nothing there about a teacher with a 1 year of experience in a PhD, for example, because it's not on there. So that's why we say that is a problem with the insertion or deletion. And then again, if I delete the only teacher with the information about 10 years of experience, then I lose that information. So this table is what we're going to see. This is not a good table, or this is not a high quality table. And then we use the process of normalization. We normalize. And the normalization, we will divide the table. We will split the table in 2 tables. Now, it's not at will that we will do that or whatever we think it makes sense. We're going to follow procedure that is going to be based on functional dependencies. So we're going to spend a lot of our time in this chapter identifying functional dependencies and uh, inspecting the current normal form of a table. And on that, we will then we will divide. So here, for example, a good design or solution, and we will see that later why, will be that teachers can become now 2 tables. So one is probably for salaries, in which we have years of experience and high degree, which determines salary. And then the other is basically the teachers or the employees that has the ID, the name, date of birth. And then if I want to know the salary, for example, we just together will be like a kind of the following key, the years of experience and high degree. We go to this table and then we determine the salary. And then in this table, the years of experience and the high degree will be uh, the key for the table. So the table teacher, which was in a good table because of the problem that we found with the functional dependency, we divided into 2 tables. Okay. So I have been talking about functional dependency, so now I just want to give you a definition, but basically what it means is a set of attributes together. When they have that value, they uniquely identify the value of another set of attributes. And we have a formal definition here. So this is the definition, which it says here, let R is the name of my relation that has attributes A1 up to In, be a relation schema. So X and Y are the subsets of that the attributes that are in R, and then we say that X functional determine Y, if basically what it means is the values on there determine the values on the other side. And the way that we say here is we are projecting T is the tuple, so there is a tuple in which the value of X in those 2 tuples is the same. Then this says if that's the case, then the value of Y in those 2 sides should be the same. For example, we go back to the teacher's example, where it says here, for example, the X will be my years of experience and my degree. So for example, if I have somebody with his 2 years and a bachelor's, and then I find another one with 2 years and a bachelor, and decide which is the Y salary should be the same. So it wouldn't be a functional dependency. We have one that is 2 years teaching experience and the bachelor's, and the same here, and the salaries are different, then there is not a functional dependency. So that's what it means. So this is the formal definition. Now there are other ways of uh, understanding this. So for example, X is a subset, and then this is the way that we will be using in this chapter. So X functionally determines Y. And there are other possible the explanations for the definition that we have, and we're just gonna go into an example, and then after that we will talk about how that we determine uh, or identify functional dependencies. So in uh, well, here there is an interesting uh, observation that we can see, that this looks like I mean that close to the concept of a key, that we say if an attribute determines the other. But remember, what we're talking about is a subset. It's not determining the value of all other attributes. For example, if we got with years of experience and bachelor's, it doesn't determine what is the name or the address of that person, right? But something that it talks about here is if X is a super key of R and Y is any subset, then we can see that that will always functionally determine the other attributes, right? So that will always be the case, that uh, that will be always true in for table, because that's the idea of a key. I mean, if the value, once we got the information about the key, for example, if we got a social security and name, you can determine any other attributes. So that's something that we can say that would be a trivial functional dependency. Let's finish this tutorial with just one example using an instance, which is the following. So now, I just need to make an observation that we do not identify functional dependencies by inspecting just an instance of the table. I mean, we will discuss that in the next tutorial. But let's see here if this hold over this instance. So for example, can A functional determine B? So what we check here is we're going to say A1, there is an A1 here. So the definition says when these are the same values, then they should be the same values here. So here the answer is no. Then can A determine C? So we're going to do the same. So A1, A1, when this is the same, is C1 and C1. Now A2 and A2, C2 and C2, A3 is C2, so there is nothing to contradict A3. So here we say yes. Can C determine A? No, C1 and C1 here, and then we got two possible values for, I'm sorry, when the C determines A. So C1, C1, A1, A1, yes, C2, C2, A2, A2, okay, yes. So remember, so once these match, no, I'm sorry. There is a problem here with the C2. C2, C2, and C2. So now we got an A3 here. So that contradicts. It should be A2, A2, A2. Okay, so this is a no. Now A determines D. Here we have a problem. A1 determines, it gives D1 and A1 D2. So this is a no. And now A2, I mean B with D. So here B1, B2, B2, here 3. Here we got a problem with B3. B3 gives D3, and B3 gives us D4. So this is another no. And finally, A and B together. So A and B determines D. So here A1, B1. There is no other A1, B1. That's unique. A1, B2. That's unique. A2, B2 is unique. A2, B3 is unique. A3, P3 is unique. So yeah, the answer is yes. Okay, so on the next tutorial, we will check how is that we identify functional dependencies. Thank you.